In physics, a gravitational field is a model used to explain the influence that a massive body extends into the space around itself, producing a force on another massive body. Thus, a gravitational field is used to explain gravitational phenomena and is measured in Newton per kilogram. In its original concept, gravity was a force between point masses. Following Newton, Laplace attempted to model gravity as some kind of radiation field or fluid. And since the 19th century, explanation for gravity have usually been taught in terms of a field model rather than a point attraction. In a field model, rather than two particles attracting each other, the particles distort space-time via their mass, and this distortion is what is perceived and measured as a force. In such a model, one states that matter moves in certain ways in response to the curvature of space-time, and that there is either no gravitational force or that gravity is a fictitious force. In classical mechanics, as in physics, a gravitational field is a physical quantity. A gravitational field can be defined using Newton's law of universal gravitation. Determined in this way, the gravitational field G around a single particle of mass m is a vector field consisting at every point of a vector pointing directly towards the particle. The magnitude of the field at every point is calculated applying the universal law and represents the force per unit mass on any object at the point in space. Because the force field is constructive, there is a scalar potential energy per unit mass at each point in space associated with the force fields. This is called gravitational potential. The fields themselves in general relativity represent the curvature of space-time. General relativity states that being in a region of curved space is equivalent to accelerating up the gradient of the field by Newton's second law. This will cause an object to experience a fictitious force if it is held still with respect to the field. This is why a person will feel himself pulled down by the force of gravity while standing still on the Earth's surface. In general, the gravitational fields predicted by general relativity differ in their effect only slightly from those predicted by classical mechanics, but there are a number of easily verifiable differences, one of the most well known being the bending of light in such fields.